You look up on a clear night and see a pale structure across the sky. It has a soft edge. It runs for a long distance over you. It is the Milky Way. It looks broad and near. It looks central to the night. Most people carry a simple picture of the sky. A horizon, a dome, bright points, a band that shows up when the air is dry and the lights are few. That band looks like a main feature. It is present in memory as a fixed part of night. It is easy to notice. Maps of the sky repeat that impression. Many maps place the band in a strong line. They draw the sky as a full oval. They draw the Milky Way as a bright stripe across that oval. The stripe feels central because the map makes a continuous frame. Small charts do the same in a simpler way. They mark the denser star areas. They label the parts that show more light. The band stands out. Your eye treats it as important. Planetariums and apps do it again. A projection wraps above you. The band crosses the room. It appears as a long track. It feels like the main axis. If you carry binoculars, the effect grows. Stars are dense along the band. There are clouds and lanes. You pass from sparse fields to rich fields. The rich fields sit along this single path. This is ordinary experience. It takes no equipment to notice. It comes from where we are. We are inside the broad disk that creates the band. That placement makes the band seem large. The disk is the Milky Way. At the scale of the Milky Way itself, the diameter is about 100,000 light-years. That scale is big to us. That scale is the full extent of our home galaxy. Most of the stars you see live within it. On that scale, the Milky Way fills the map. A map that shows the disk at about 100,000 light-years across gives the Milky Way the whole frame. The galactic center sits in one direction. The outskirts sit in the other directions. The band is not a stripe on the map anymore. It is the map. At that size, it feels right to treat the Milky Way as the main thing. You can move from inner regions to outer regions. You can describe arms and gaps. The band you see at night is now a cross-section. The distance you traverse is about 100,000 light-years. The Milky Way retains the central role. If you then step out one level, the view changes. You now include the nearest large neighbor. It is Andromeda. The separation is about 2.5 million light-years. That number is not the size of a galaxy. That number is the gap between two of them. You have left the Milky Way scale. At a map that spans about 2.5 million light-years, the Milky Way becomes one disk in a pair. It no longer fills the frame. It no longer sets the line. It sits offset from the center. It shares the map with Andromeda. This is the first moment the Milky Way becomes small in appearance. It is not smaller in itself. It is smaller compared to the reach of the map. At about 2.5 million light-years, the map is many times wider than about 100,000 light-years. The Milky Way takes a small fraction of the space. Survey images at that scale show clean points or small disks. The night band is gone. The sky is not a dome here. This is a map drawn from outside. The Milky Way holds shape as a galaxy. It looks contained. Andromeda looks of similar size. The gap between them is large compared to their widths. If you step back again, the shape blur changes once more. You now think in a reach of about 1 billion light-years. That is not a local neighborhood. That is a deep survey. It contains many groups and clusters. It is a very broad frame. On a map that spans about 1 billion light-years, a single galaxy is a point. The Milky Way is not visible as a shape. It is not a stripe. It is not a disk. It is a point folded into a cloud of points. You need a label to find it. Observers build such maps by noting positions of many galaxies. They fill the frame with dots. Patterns appear only when you step far back. The Milky Way disappears into the field. It is smaller than the map features you now notice. It is part of the background. This move between scales is simple to state. At about 100,000 light years, the Milky Way is the map. At about 2.5 million light years, the Milky Way is one of two main disks. At about 1 billion light years, the Milky Way is a dot. The numbers do the work of the frame. It is normal that the eye treats the Milky Way as central when looking up. The arc runs through the sky and suggests a main direction. It is a local effect. It comes from being inside the disk. It is not wrong. It is just a view at one scale. All sky images show the same bias. The oval is full of stars, and the band splits it. This is just projection. It is not a sign of central placement in space. It is a sign of orientation. The disk is the densest line of light, and the map shows it most clearly. Photographs of the night sky increase this sense. Long exposures bring out the texture. The Milky Way looks like the main structure. Less of the rest of the sky shows. The dynamic range guides the eye to the bright, dense band. The band appears to define the sky. But if we hold the three scales in mind, the change stays clear. There is the scale of about 100,000 light years. There is the span to Andromeda at about 2.5 million light years. There is the wide field of about 1 billion light years. The Milky Way moves from filling the view to being a point, not because it changes, but because the frame changes. A map drawn at this scale of about 100,000 light years cannot see beyond the Milky Way. The farthest edge of the map is still inside the disk. The band remains central by design. The galaxy defines the boundary. A map drawn at the scale of about 2.5 million light years must show the gap to Andromeda. The Milky Way is an object within the frame. It does not enforce the frame. The gap acts as a reference. The Milky Way sits in a relationship rather than dominating the picture. A map drawn at the scale of about 1 billion light years uses a much larger grid of positions. The Milky Way is not special in this map. It is counted among many. It has the same symbol as the others. It does not adjust the layout. This sequence is visible in public atlases and survey pages. The same object looks different depending on how far the map extends. The Milky Way can be a band, a disk, or a point. Each view is consistent. Each view is a slice of the same space at a different depth. Some maps of the Milky Way at about 100,000 light years get drawn from inside. They use the band and star counts. They use gas lanes to trace structure. They infer the general outline. The detail is sharp along the band because that is where the stars lie. Some maps at about 2.5 million light years use photographs of Andromeda and the Milky Way compared. They show two disks roughly similar in size. They mark the separation. They note the span between centers. The focus is on the gap. Some surveys at about 1 billion light years mark galaxies as dots. The Milky Way is not singled out. It is one dot. The map uses the same scale for all. The frame is so large that local detail is lost. The interest shifts to patterns of dots. This shift in what seems important is a visual effect. It is not an argument. It is not a claim about value. It is about scale. The numbers about 100,000 light years, about 2.5 million light years, and about 1 billion light years set how the Milky Way appears. You see this also in how astronomers compose press images. A shot inside the Milky Way looks expansive. A shot of Andromeda and the Milky Way together looks balanced. A plot of many galaxies out to about 1 billion light years gives no special weight to our own. Each image uses a distinct span. Some listeners leave comments about where they are and what time they are listening. They say a city or a rural place and the local hour. It notes the context of the night. It does not affect the maps. When you plan a night under darker skies, you expect the band. You expect it to be noticeable. That expectation is met. The band lies as a long feature passing across. It is hard to miss. It demands attention because it is the most crowded line of stars. The persistence of the band in old and new observations builds a strong mental model. The Milky Way feels like the sky itself. It is the thing you notice first. It sets the field. It establishes where your attention goes. It becomes the default baseline. Once you first see the wider frame, that mental model loosens. It does not vanish. It shares space with the image of the Milky Way as a single disk. The number about 2.5 million light-years attaches to the new display. It supplies a sense of reach beyond our disk. Then the deeper frame loosens it further. You see field after field of galaxies. The number, about 1 billion light-years, anchors the deep reach. There is no one galaxy that asserts itself. The Milky Way is in that list. It does not lead. This is not an attempt to minimize what we live in. It is a description of how the Milky Way looks when you change the map width. The object maintains its size at about 100,000 light-years. The map width changes from about 100,000 light-years to about 2.5 million light-years, and then to about 1 billion light-years. The fraction occupied by the Milky Way shrinks. Textbooks sometimes use a series of panels. Each panel has a different span. The left panel sits at about 100,000 light-years. The middle panel spans about 2.5 million light-years. The right panel goes out to about 1 billion light-years. The same object goes from detailed to small to a symbol. If you think about how this looks in a planetarium, it also lines up. The dome view shows the band. Then the display pulls back so that the band becomes a narrow strip and the disk emerges. Then the pull continues and the sky fills with galaxies. The steps correspond to the 3 numbers. The Milky Way moves from dominant to minor. Your mental anchor points can shift with repeated exposure. You can hold the band view in one place in your mind. You can hold the paired disk view for the about 2.5 million light-year span. You can hold the wide survey view for the about 1 billion light-year span. Each view has its own logic. Each view is correct for its scale. At the first scale, the band is central because you are inside the disk. The entire sight line lives within about 100,000 light-years. The Milky Way dominates the sky because it supplies most of the stars you can see. This is not abstract. It is visible. At the second scale, the band is a narrow feature within a larger context. The frame now includes the gap to Andromeda at about 2.5 million light-years. The Milky Way is one disk in a 2-disk picture. The gap between them is larger than either disk. The Milky Way does not occupy most of the map. At the third scale, the disk is no longer resolved. The map reaches about 1 billion light-years. The Milky Way is indistinct in the crowd of points. It cannot set the reference. It cannot impose a main direction. It is part of a collection. Camera fields mirror this idea as well. A small field within our galaxy shows structure. A wider field that can still image Andromeda shows 2 shapes at the edge of the frame. A very wide survey field shows only points. Each device responds to a different span in the 3 numbers. This framing affects how star counts feel. In the band, star counts feel high. In the 2-disk frame, star counts from the Milky Way feel like one entry among neighbors. In the deep frame, star counts per galaxy do not appear at all. The map does not carry that detail. It carries positions out to about 1 billion light-years. When you hear someone say that the Milky Way is large, they are often referencing the about 100,000 light-year scale. When they say the local group, they are referencing the about 2.5 million light-year gap to the nearest large partner. When you hear the phrase large-scale structure, it often refers to the region out to about 1 billion light-years. The words echo the size of the frame. In backyard practice, the first 2 frames are most intuitive. You see the band. You may have seen Andromeda as a dim patch. The about 2.5 million light-year separation is a known fact. It gives a feeling of space between major systems. It forces the Milky Way to share the scene. The third frame comes from compiled data. You do not see about 1 billion light-years at once. You gather positions over many fields. You place them together. The result is a plot with many points. The Milky Way is one of those points. It holds no clear mark. The result of all this is not a hidden trick. It is a method of seeing. Change the span, and the role changes. Keep the specific spans in mind. About 100,000 light-years for the Milky Way. About 2.5 million light-years to the nearest large neighbor. About 1 billion light-years for a deep volume. The Milky Way goes from setting the frame to being included within it to vanishing into it. If you study star charts at home, you can notice which scale they imply. If the chart shows a thick belt through the center, it is likely anchored to the about 100,000 light-year perspective. If it shows two large disks with a measured gap, it is tuned to about 2.5 million light-years. If it shows a scatter of distant galaxies, it is tuned to about 1 billion light-years. The same logic governs how museum displays guide you. They first show the band and call it home. They then show the nearby large galaxy and the space between. They then show a pattern of many galaxies in a large volume. The repetition sets the sense that the Milky Way shrinks in importance as the frame widens. This is not a matter of technical definitions. It is a matter of what the map includes. A map that only includes the Milky Way will be dominated by it. A map that includes the Milky Way and Andromeda will be split between them. A map that includes a volume out to about 1 billion light-years will not favor either. It will not favor any one galaxy. Hold those three spans. See how the Milky Way shifts from the band overhead to a disk beside another disk to a point among many. Keep the word simple. About 100,000 light-years. About 2.5 million light-years. About 1 billion light-years. The numbers anchor the change in view. The Milky Way looks large to us at night. It is near because we are inside it. It is about 100,000 light-years across. That size sets the scene for our sky. That size does not change with the view. There is a reason the size of the Milky Way stays the way it is. The stars, gas, and all the mass in the galaxy pull on each other. That pull holds the system together. It holds it near the same span of about 100,000 light-years. The Milky Way is a bound system. Because it is bound, its size is fixed in the way we care about here. It can change slowly in detail. It can gain or lose material. But its general scale remains about 100,000 light-years. It is confined by its own attraction. Now look beyond the Milky Way. Consider distances that reach out to about 2.5 million light-years and further. The distance to Andromeda is about 2.5 million light-years. The region that includes both is a larger setting. Inside that region, some pieces are tied together. Outside that region, pieces are not tied to us. There is a second effect that appears once you look beyond such bound regions. Large-scale distances grow over time. This is not a growth inside a galaxy. This is a growth between separate systems that are not held together. The farther apart they are beyond bound regions, the more this growth shows. Hold the two ideas without mixing them. Inside the Milky Way, the system is bound. Its scale stays around about 100,000 light-years. It does not grow because the pull holds it. Beyond the range where gravity binds systems together, the spaces between those systems expand. This growth acts on distances like the ones that fill a map out to about 1 billion light-years. This contrast is the core cause for how the Milky Way becomes tiny on the largest maps. One part stays the same. The other part grows. The constant part is the size of bound systems such as the Milky Way at about 100,000 light-years. The growing part is the separation between unbound structures. Once you look at spans like about 1 billion light-years. Say it in the simplest way. The Milky Way is held together. The space between far-off systems stretches. When you draw a map at small scale, you see the held-together part. When you draw a map at large scale, you see the stretching part. The Milky Way keeps its size, while the map keeps getting larger. If you drifted, return to the numbers. About 100,000 light-years marks the size of the Milky Way. That size is held by its own pull. About 2.5 million light-years marks the gap to the nearest large neighbor. That gap sits inside an area where binding still matters. About 1 billion light-years marks a span where the growth of distance is visible. The larger the span, the more growth has acted. Another simple pass through the same idea. Bound systems do not expand with the universe. The Milky Way is a bound system. It stays near about 100,000 light-years. The very large gaps outside bound regions do expand. A map that reaches to about 1 billion light-years compares the fixed size of bound systems with the larger, expanding gaps. You can hear the cause and effect in one chain. Gravity binds some structures at small scales. Bound structures resist the stretching of space. They stay near a fixed size, like about 100,000 light-years. On scales beyond bound regions, the stretching of space increases the separation of structures. The distances that fill a map of about 1 billion light-years grow over time. Because of this, the Milky Way shrinks in relative terms when placed in a largest frame. The phrase shrink in relative terms here is about maps. It means the fraction of the frame the Milky Way takes up is smaller. The bound size remains about 100,000 light-years. The frame grows to include separations shaped by the growth of space. Once the frame is something like about 1 billion light-years, the Milky Way occupies almost no area on the map. If you drift it again, this is the anchor. Some things hold together. The Milky Way holds together. Its size sits around about 100,000 light-years. The giant emptiness between unbound systems does not hold. It grows. That growth matters once your frame covers about 1 billion light-years. You can also think about the middle step as a check. At about 2.5 million light-years, the frame is small enough that binding is still involved. Two large galaxies share a region where pull matters. This region resists expansion as a whole. This is why inside such regions, you do not see the growth of space change the distances yet in a clear way. The bound parts hold each other near. Then step out to about 1 billion light-years. You now include many regions that are not bound to each other. The growth of space has acted between them. The result is a pattern of separations that are larger than they would be without that growth. The Milky Way, with its fixed size, is small compared to those separations. The key is not an equation. The key is the nature of the two regimes. Bound systems keep their scale. Unbound separations grow with the universe. This dual behavior is enough to explain the visual effect we described in the first part. The Milky Way is big in itself, but tiny against the canvas of the growing distances. Another way to say it: the size of the Milky Way is anchored by its own gravity. The background canvas you draw it on becomes larger with time if you include distances that are not held. When your map includes about 1 billion light-years, your canvas includes a lot of that growth. The galaxy is the same size on any given day. The canvas is not. Hold the three numbers as a way to feel this. About 100,000 light-years is a bound size. About 2.5 million light-years is a nearby gap where binding can still set relations. About 1 billion light-years is a wide span where the expansion of space has agency. The relative scale of the Milky Way changes across those frames because one scale follows binding and the other follows expansion. If you need the cause broken down once more: cause, gravity keeps a galaxy together. Effect, its size is about 100,000 light-years and does not participate in the general stretching. Cause, space itself stretches at large scales. Effect, separations between unbound systems increase over time. Put the two together in one map. and the fixed part looks smaller and smaller as the growing part defines more of the frame. You do not need a constant to hold this picture. You do not need to recall any formula. You can keep the picture informal and correct. A bound galaxy is fixed in size. The universe expands on large scales. Comparing the two at one time gives you a strong difference. This difference is the reason the Milky Way is dwarfed in deep surveys. Attach this now to the specific spans. The Milky Way is about 100,000 light-years across. That is the fixed size. The gap to the nearest large galaxy is about 2.5 million light-years. That is inside a region where binding is still relevant. The span out to about 1 billion light-years covers distances between many regions that are not bound together. Those distances have felt expansion. A map that spans this region must reduce the Milky Way to a symbol. A small re-anchor for drifting listeners. We are not changing what the Milky Way is. We are changing what we compare it against. When we compare it against nothing but itself, it is the only thing present. When we compare it against a region where binding ties neighbors, it becomes one unit among a few. When we compare it against a reach of distance that grows over time, it becomes small because the background has grown. There is a question of how to phrase the growth. You can simply say that space between unbound systems increases. There is no need to discuss how we measure it. There is no need to discuss precise rates. The effect is enough to state, the farther and larger the span you plot, the more stretched the distances between unbound objects become. The Milky Way does not track that stretch internally. Return again to the chain. Bound systems resist expansion. The Milky Way is bound. Therefore, its physical size remains about 100,000 light-years. Expansion acts on scales beyond bound regions. Therefore, a map that reaches to about 1 billion light-years displays distances that include the effect of expansion. Therefore, when both are placed on one plot, the Milky Way occupies a very small part of the plot. The local step at about 2.5 million light-years is instructive as a pivot. This is where people often first think beyond the Milky Way. It is near enough that we do not need to discuss broad expansion to place it. It is far enough that the Milky Way is no longer the entire frame. It is the first hint that our fixed size will soon be overshadowed by the separations outside. Push out again to about 1 billion light-years. Stop and hold that span. Within that volume, most pairs of far-flung structures are not bound to each other. Their distances have increased since earlier times. On such a map, the Milky Way keeps its old size, while the map embeds many expanded gaps. The contrast is stark. It drives the visual smallness of our galaxy on the page. If you drift again, come back to one sentence. The Milky Way keeps its size because it is held together, but the large-scale distances you plot keep growing, so the Milky Way looks tiny on those plots. This is cause and effect. There is no extra detail needed to hold it. You can also say that the bound size is a local rule, and the expansion is a global rule. The local rule governs about 100,000 light-years. The global rule governs spans like about 1 billion light-years. In between, at about 2.5 million light-years, both rules matter in different ways depending on what you include. But the theme holds. Fixed sizes within, expanding distances without. The reason to repeat this is simple. The mind tends to treat large familiar things as central. The night sky tells you that the Milky Way is large and central. That impression comes from being inside a bound object. The larger map tells you that distances beyond bound regions do not care about this internal size. They expand anyway. So your central structure contracts in relevance as your map honors those expanding separations. Avoid the urge to add more mechanisms. The core mechanism is enough. Binding keeps some sizes fixed. Expansion increases large separations. Comparing the fixed segment at about 100,000 light-years to the expanding canvas out to about 1 billion light-years produces an apparent smallness. This is not because the Milky Way shrinks. It is because the comparison changes. One more time in plain steps. Bound systems keep form. Unbound distances increase. The Milky Way is bound and near about 100,000 light-years across. The map out to about 1 billion light-years includes distances that have increased over time. The ratio between the two grows. On that map, the Milky Way becomes tiny. If you need a picture with fewer words, a galaxy holds itself together. The universe stretches the spaces between far-off galaxies. On a small map, the first statement is all you see. On a large map, the second statement dominates. The first is still true, but it matters less for the frame. Focus again on the three spans as handles. About 100,000 light-years is where holding wins completely. About 2.5 million light-years is where holding still matters for the local environment. About 1 billion light-years is where the expansion of distances has set the space in between. The Milky Way does not grow to match the canvas. The canvas grows around it. You can also think of time quietly. The fixed size at about 100,000 light-years is steady across your lifetime. The distances in a map of about 1 billion light-years have evolved over cosmic time. The large-scale separations are larger now than in the past. That is why the Milky Way takes up a smaller and smaller fraction of the whole as you consider larger and larger frames built at the present time. The two regimes coexist without conflict. They happen in different places and affect different things. Inside the Milky Way, you can ignore expansion for the purpose of size. Outside, when you span to about 1 billion light-years, you must include expansion to understand why the spacing looks the way it does. This split is simple and sufficient. Repeat the core in the simplest sequence. The Milky Way is bound. Bound systems keep size. Large-scale space expands. Expanding separations make the canvas larger. On the canvas of about 1 billion light-years, the Milky Way is small because the canvas has grown and the galaxy has not. If you drift, you can come back to only the numbers. About 100,000 light-years for the Milky Way. About 2.5 million light-years to step beyond it, while binding still matters. About 1 billion light-years to reach scales where expansion defines the spacing. Put them in order, and the explanation follows. This is why the night sky can be honest and still give a biased sense of scale. It shows you the bound interior. It does not show you the expanding exterior by eye. You need other maps for that. When you switch maps, you switch rules. The fixed size of the galaxy meets the expanding reach of space, and the galaxy becomes a small mark. There is no need to complicate the language. Keep it tight. Bound systems keep size. The Milky Way is bound and about 100,000 light-years across. Unbound distances expand. A deep map to about 1 billion light-years is full of distances that had expanded. The Milky Way is constant against a growing background. This is the single mechanism that explains the shift from large and central in the night sky to tiny and hard to locate in a deep survey. The Milky Way remains what it is. The frame you choose changes which physical rule matters. At small scales, binding controls what you see. At large scales, expansion controls what you see. If we now return the numbers to the front, we can set the picture again before moving through another rephrasing of the same cause and effect. You have looked at a city from far away. The buildings did not resolve. You saw a scatter of lights. Each point stood in for blocks, streets, and roofs. You accepted this because distance made detail irrelevant. A wide sky survey works the same way, but with distance measured in light years. A single galaxy is about 100,000 light years across. The space between large groups of galaxies is about 1 million light years. A regional survey may span 100 million light years, and a deep survey may reach 1 billion light years. At those scales, a galaxy becomes a point because its internal structure is too small to draw. Nothing about the galaxy itself has changed. It still has arms, dust lanes, and star fields. What changes is the scale of the map. A chart that spans 100 million light-years cannot also show 100,000 light-years of detail for every object. If it tried, the image would blur into noise. The galaxy becomes a dot, so the larger pattern can remain visible. This effect becomes stronger at greater distances. On a map reaching 1 billion light-years, even clusters of galaxies shrink to points. A cluster that spans 1 million light-years is small compared to a billion. The ratio forces compression. Extended objects collapse into markers, so the map can show the structure of the region as a whole. The cause is not mystery or loss of information. It is the choice of scale. The instrument measures light from a fixed patch of sky. That patch has a constant angular size. The farther away an object is, the larger the physical region that patch represents. At 100 million light-years, a single patch can cover a region comparable to the size of a galaxy. Mapping requires a grid. Each grid cell represents one measured unit of space. If a cell spans 1 million light-years at the survey distance, any galaxy that fits inside that cell must be represented by a single position. The grid cannot show structure smaller than its own size. It can only show where objects are and how many fall into each cell. Smaller cells reveal more detail. Larger cells reveal less. When the goal is to map 100 million or 1 billion light-years, the cells must be large enough to cover the region efficiently. That choice removes internal structure, but reveals large-scale patterns. The use of points is not a shortcut. It is an honest record of what the grid can support. A dot does not deny spiral arms. It simply states that spiral arms are smaller than the sampling unit. The dot marks the center of light and the presence of the object without drawing its shape. A few numbers keep the logic grounded. 100,000 light-years describes the size of a galaxy. 1 million light-years describes the spacing between major groupings. 100 million light-years describes the scale of regional surveys. 1 billion light-years describes deep surveys. These numbers determine what can and cannot appear on the map. You experience the same effect when zooming out on a map of Earth. At close range, you see streets and trees. At country scale, streets disappear and cities become points. Zooming out is a choice. It trades detail for pattern. A sky survey does the same, using vastly larger distances. A survey begins with a field of view, like a window. At 100 million light-years, that window spans roughly 1 million light-years in physical size. It can detect galaxies and the gaps between them, but not internal structure. When many windows are tiled together, the result is a mosaic of positions. The map shows a web built from points, not shapes. Holding the ratios steady helps. A galaxy is 100,000 light-years wide. A sampling bin is 1 million light-years. A survey region is 100 million light-years. A deep field reaches 1 billion. Each step up loses one kind of detail and gains another kind of pattern. This is not a flaw. It is the purpose of scaling. No additional physics is required to explain this. The instrument selects a patch. The analysis selects a grid. The presentation selects a symbol. At wide scales, the symbol that fits is a point. That symbol is truthful, because the grid cannot carry finer detail. Wide surveys are censuses of light. Like counting cities instead of people, they record positions and brightness, not internal layout. Catalogs list coordinates and intensities because the survey scale demands it. Pictures of individual galaxies belong to different studies with different goals. If the survey were closer, the patch would shrink in physical size. A galaxy would spread across many cells and appear extended, but that would no longer be a wide survey. At 100 million or 1 billion light-years, the dot remains correct. The ratios make this inevitable. 100,000 is 1/10 of 1 million. 1 million is 1/100th of 100 million. At each step, smaller structures fall below resolution. They remain visible as presence, not texture. It is natural to feel that something is lost when a galaxy becomes a dot. But at this scale, the question being asked is not about arms or dust. It is about where galaxies gather and where space is empty. That pattern lives on scales of millions of light years. The dot provides exactly the information needed. Symbol size is chosen only for readability. Making dots larger or smaller does not change the underlying logic. The decision to use dots comes from scale, not from style. At greater distances, the same effect repeats. At 1 billion light years, a fixed angular window covers many millions of light years. Multiple galaxies can fall into one window. The measurement averages them. The result is again a point marking a location. Distance alone drives this compression. Resolution simply means the smallest separation that can be distinguished. On a wide map, that separation measured in light years is large. Objects closer than that merge. The map records one marker instead of two. This is expected, not misleading. Maps are choices. A map covering 100 million light years keeps positions and discards internal shape. A map covering 1 billion light years keeps distributions and discards even cluster extents. In both cases, a galaxy becomes a point because the map has no room for more. This is why wide surveys appear as scatter plots. Each marker represents a galaxy or small group. Dense regions show structure. Sparse regions show voids. Internal galaxy detail would not change the pattern, so it is excluded. The dot is a form of compression. Compression removes detail while preserving what matters at the chosen level. On wide surveys, what matters is density and arrangement across enormous distances. Details at 100,000 light years are compressed away. Changing the numbers changes the picture. A survey spanning 10 million light years could afford more structure. A survey spanning 100 million cannot. The need for dots returns as soon as the scale grows. The logic extends naturally. Clusters appear as clusters of dots. Superclusters appear as denser regions. Arms and disks never appear because they are far below the scale of interest. The map is not incomplete. It is tuned. It answers a specific question: how matter is arranged across vast regions of space. For that question, points are sufficient and correct. Think again of a city seen from far away. The lights do not lie. They show where things are at that distance. If you move closer, detail appears. Sky surveys work the same way, using distances of 100,000, 1 million, 100 million, and 1 billion light years. Once these numbers settle in your mind, the maps become easy to read. You know when a galaxy must appear as a dot. You know when clusters dissolve into patterns. The representation follows directly from scale. A dot is not a loss of meaning. It is meaning at the right level. Stand on the hill again. The lights are points. You do not fight that. You accept that the distance sets what you can see. The sky survey obeys the same limit, expressed in larger numbers. The same four distances guide your sense here. A galaxy spans about 100,000 light years. The space between large groups is about 1 million light years. A regional map covers about 100 million light years. A deep field reaches about 1 billion light years. These are the scales that matter for this explanation. They repeat because they fix what can be shown. Pick one cause and sit with it. The cause is scale choice. If you choose to map 100 million light years, you choose to let 100,000 light-year shapes collapse. You choose to let 1 million light-year gaps be your finest usable spacing. This is not a flaw. It is a condition of the map you have decided to make. Think about the instrument's window once more. The window sees a patch. At 100 million light-years, that patch spans roughly 1 million light-years. The window cannot reveal details smaller than itself. It can only register that something is in the patch and where the patch lies. When you step that window across the region, you collect positions. Those positions are then plotted as points. On a map that spans 1 billion light-years, the same window spans more in physical size. It may cover 10 million light-years or more. That is greater than the 1 million light-year gap you had been using as a mental spacing. At that range, many objects blend within one window. The map still plots points because the consistent unit across the map is the window position, not the individual galaxy shape. Return to the grid picture. Imagine dividing the space into blocks, each 1 million light-years on a side. Inside each block, the internal structure of a galaxy would be small. 100,000 light-years is 1/10 of the block width. The map records whether the block contains a galaxy. It does not record the arms inside the galaxy. That decision yields a dot for each occupied block. If you reduce the block to 100,000 light-years, you could draw edges and curves. But to span 100 million light-years, you would need 1,000 blocks across each dimension. The map would become too large to hold easily. You would lose the wide view. The very act of creating a wide survey pushes you back to blocks of 1 million light-years or more. The point representation follows. This does not require special terms. It is the same logic you use when switching from a street map to a country map. On the street map, a block is the basic unit. On the country map, a city is the basic unit. In the sky, on the close map, a galaxy fills many cells. On the wide map, a galaxy occupies one cell. The cell is then drawn as a point. Repeat the ratios with calm certainty. 100,000 to 1 million is 1 to 10. 1 million to 100 million is 1 to 100. 100 million to 1 billion is 1 to 10. Each jump reduces what you can depict of the smaller scale. Each jump increases the field you can hold at once. The dot survives each jump because it is the simplest truthful symbol. When you see a printed catalog, you may notice that each entry reduces a galaxy to numbers and words. Position, brightness in a band, perhaps a rough size if the survey allowed it. On the widest maps, even the size becomes uncertain. The position remains robust. That robustness is why the dot is reliable. The position does not require resolving the arms. It only requires locating the center within the window. If you change nothing but the distance to the target, the physical size behind each sample changes. This is the heart of the mechanism. At greater distances, the same instrument samples larger physical chunks. The 100,000 light-year structure becomes a detail inside a larger sample and cannot be separated. The map must mark a center and move on. You can picture the field as a lattice. Each junction is 1 million light-years apart. At each junction, you ask whether a galaxy lies within the nearby volume. If yes, you place a point at the known coordinates of that center. If a galaxy sits halfway between junctions, you plot it midway between points on the map. The shape does not enter. The bins structure the data. The plot is therefore a set of points. Nothing else needs to be layered on top. The sample window, the distance, and the chosen field set the outcome. If the field is 100 million light-years across, the window at the typical distance feels like 1 million light-years. The galaxy of 100,000 light-years is 1/10 of that. The natural map reduces it to a dot. Carry that through to 1 billion light-years. Now, the same window feels like 10 million light-years. The 1 million light-year spacing between large groups is now a small fraction of the window. Several groups and many galaxies might fall within a single pointing. A dot now stands for a blended center, or for the average location of light within the window. The plot remains a field of points. The reason remains the same. You may be tempted to think that adding more sensitivity would bring back shapes. Sensitivity adds faint things. It does not change the physical size of the window at a given distance. The arms remain too small compared to the window. The dot persists. though you may add more dots as faint galaxies appear. The mechanism is unchanged. Likewise, longer exposures do not change the scale. They change signal, not resolution at this level. The wide map continues to compress shapes into positions. The 100,000 light-year features stay below the resolvable scale for a map spanning 100 million or 1 billion light-years. The repeated numbers keep your judgment steady. When you look at a point map, your eye connects points into lines. It sees filaments and walls. These are arrangements on scales of tens of millions of light-years. The map is built to reveal those. It is not built to reveal the curves of a single galaxy's arms across 100,000 light-years. That is a different map for a different purpose. Consider a common product from such surveys. A wedge diagram shows a slice extending to 1 billion light-years. The slice displays thousands of points. Each point is a galaxy. The spacing along the slice is dominated by distances and selection. The shape of each galaxy does not appear. It is absent because it does not matter for this view. The mechanism you have been following explains this elegantly. The scale does the deciding. There is a firmness to this. You do not have to negotiate with the numbers. 100,000 compared to 100 million is a thousand-fold difference. That difference enforces a representation. It enforces dots. If you try to force more into the map, you invite confusion. The deliberate choice to keep dots is a choice to keep the map legible and truthful. Return again to the grid at 1 million light-years. Any galaxy will sit within a handful of such cubes. The center will sit within one. The map will mark that. If two centers are separated by less than 1 million light-years in the plane of the sky at the survey distance, the map may not separate them. It may show one point where two exist. At 1 billion light-years, the blending is stronger. The logic has not shifted. The environment has. If you move to a closer field, the blending eases. At 10 million light-years, the 100,000 light-year shape is 1% of the field. You can begin to render more than a point, but the assignment here does not move to that field. It stays with 100 million and 1 billion light-years. It stays with the idea that an object 10 times smaller than the basic sample cannot be cleanly depicted. Think about the thickness of the pen when drawing the map. The smallest mark you can make has a size. On a conceptual map of 100 million light-years, the dot you draw might stand for 1 million light-years across, simply because that is the least crowded representation. The physical thickness of the mark is a metaphor for the sample window size. The analogy is enough. It conveys that internal detail is smaller than the dot. It can be restful to repeat the view from the hill. The points from the city give you all you need to orient at that range. You can tell where the city ends. You can tell where it is brightest. You cannot tell the architecture. If you need the architecture, you walk closer and make a different kind of map. If you need the spread across the valley, you stay far and accept points. The sky survey accepts points because it needs the spread across 100 million and 1 billion light-years. Every extended survey uses this trade. It replaces shape with center. It replaces texture with count. It replaces small-scale variation with large-scale structure. The choice is encoded by the distances you keep repeating. 100,000 for internal structure. 1 million for separation. 100 million for the region. 1 billion for the deep field. The same numbers organize the picture. If someone hands you a map with tiny galaxy images on a 100 million light-year canvas, you will know to be cautious. Each tiny image is either symbolic or misleading. The true content is the center and the presence. The true map for that canvas is a scatter of points. The scatter is full enough to show patterns at tens of millions of light-years. It is empty of internal arms by necessity. You can inspect a single dot. You can think through what it contains conceptually. It may represent 100 billion stars across 100,000 light-years. It may represent gas and dust. None of that appears on this map. On this map, the dot is a single location in a space defined by 1 million light-year bins. You can note its position relative to other dots. That is what the map can bear. The manner of speaking about this can remain plain. You do not need to say angular size. You can say window size. You do not need to say integrate. You can say measure a patch. You do not need to say beam. You can say a field of view. The reason for the dot is clear in these terms. You measure a patch that is large in physical size at the survey distance. The object is smaller than the patch. The object reduces to a point. Repeat the scales enough times for them to become quiet in your head. 100,000, 1 million. 100 million, 1 billion. The gap between 100,000 and 1 million tells you that detail will be hard to keep at 1 million. The gap between 1 million and 100 million tells you that you can hold many spacing units on one map. The step to 1 billion tells you that the whole scene will compress further. Each step simplifies what can be shown. When you compare two maps with different coverage, you see the effect. A narrow map of 10 million light-years shows some galaxies with shape. A wide map of 100 million is a star field of points. A deeper map of 1 billion is a denser field of points. The difference across these is not the nature of galaxies. It is the size of the window relative to the objects. The representation follows. You can place this in your mind in still another way. Think of a camera with a fixed pixel count. If you widen the scene, each object takes fewer pixels. At some width, the object takes less than 1 pixel. It cannot be drawn, except as the presence of something that triggers that pixel. On the sky, the pixel at 100 million light-years is about 1 million light-years if you are using a certain window. The galaxy is 1/10 of that. It becomes a dot. This framing avoids the need to add any other mechanism. It respects that there is one cause and one outcome. The cause is scale choice. The outcome is compression of extended objects into points for wide surveys. The repetition anchors the link between the numbers and the visual. The dots are not arbitrary. They are bound to the ratios you are carrying. The mapping task then feels simple. Place dots where galaxies are. Look for their clustering. Use bins near 1 million light-years for analysis, across 100 million light-years fields. Use similar logic for 1 billion light-years fields, with the understanding that blending will be greater. The galaxy does not show its arms in this frame. It contributes its center to the pattern. People sometimes bring up exceptions. Nearby large galaxies on the edge of a 100 million light-year map might show a hint of shape. That does not disturb the general rule. It only reflects that the distance for those objects reduces the physical size of the window. The mechanism remains scale. The representation remains a point wherever the ratio remains large. The survey's summary images are often binned. The bin size is chosen to match 1 million light-year scales. The choice suppresses small-scale noise and reveals large-scale structure. The bins filled with galaxies light up as dense points. The empty bins stay dark. When plotted, you again see a spray of points. If you adjust the bin size, your view shifts a little. But within these numbers, the dot logic persists. You can think of the dot as a promise. It promises that at the chosen scale, showing only positions is enough. It does not promise detail it cannot provide. It invites the viewer to change scale if detail is required. The viewer can then look at a separate map built for 100,000 light-year structure. This separation keeps both maps honest and useful. The wide survey is quiet. It does not hurry. It sweeps windows across the sky. It stacks results. It produces a clean list of where galaxies lie within 100 million or 1 billion light-years. The processing turns those into points. The plot then shows a skeleton of the universe on those scales. The method does not reach inside any single galaxy. It does not aim to. It keeps to its lane. There is no hidden trick behind why galaxies compress to points. There is only the gap between the size of the thing and the size of what you are trying to cover. You cannot fit everything at once without changing what each mark means. The chosen mark for this job is a point. It shows location. It lets you see how locations arrange over great distances. It leaves the rest to other maps. When you let this sink in, you stop expecting more from a dot map than it can give. You read it correctly. You look at the distribution across 100 million and 1 billion light years. You trust that the choice of scale is why you see points. You trust that the same choice, if changed, would yield different maps. You keep the same 4 numbers in the back of your mind. You let them guide your expectations. The steady repetition of distances is not a crutch. It is a way to keep the mind from drifting. 100,000, 1 million, 100 million, 1 billion. Each one fits into the next. Each one suggests what to show and what to suppress. Each one implies a map type. The type in question here is the wide survey. The symbol for that type is a point. The effect of this on your sense of the universe is calming. The complexity is real. The representation is simple because the view is wide. The insight, if you were to seek it, would come from arrangement, not from internal design. But we do not press for insight. We hold to the mechanism. We hold to the scales. We accept the dots. You can walk this in any direction. Start from the dot and ask what could it be. It could be a galaxy of 100,000 light years across, at a distance such that your instrument's sample covers 1 million light years. Start from the region and ask what must the map show. It must show positions across 100 million or 1 billion light years in a way that is not crowded. The answer is again dots. So we arrive at the same picture repeatedly. Wide surveys compress galaxies into points because the region to be mapped is too large to hold their shapes. The sample windows are large in physical size at those distances. The bins are chosen to be about 1 million light years for 100 million light-year maps, and larger for deeper ones. The symbol matches the constraints. And if you wish to continue, you can. You can let the window sweep again. You can let the bins fill and empty again. You can let the points fall into place across the field again, each one a compressed presence, each one carrying only its position, across 100 million light years, across 1 billion light years, again and again, with the same 4 distances setting the terms without end.